Okay. Yes? No? Okay. Yes? All right. Yeah, sorry about that. So thanks again to the organizers for giving me a chance to participate in this exciting meeting. I'd like to cover a few aspects of how we might think about the links between deep dynamics and the surface, and in particular, the sort of deformation we see in the rock record. Now, the overall goal is to link the history of planetary evolution that's recorded in the oceanic and in the continental lithosphere to the thermal evolution of the planet, which is controlled by mantle convection, as illustrated here by seismologically inferred wave speed anomalies that we are interpreting as temperature or compositional anomalies. Now, as some of the previous speakers illustrated, the dynamics of the oceanic lithosphere are much simpler than those of the continental lithosphere, because the contributions of volatiles and of composition are much more complex, and the continental lithosphere is lighter, which means it stays at the surface for the most part and records a much longer history of deformation. So there's sort of a billion-year record in the continents. There's only about 100 million year, whatever average residence time of around 70 million years in the oceanic lithosphere, because it's constantly being recycled. And the challenge is to utilize the geological record here while recognizing that hysteresis, in terms of a memory of deformation, is quite important. And there's different ways of going about that. And one, just sort of animating this again, that is illustrated here on the right, which are the predictions of a global mantle convection model that has prescribed continental floats that you can see here in these orange outlines. But within the oceanic domain, which is colored by a heat flow inferred seafloor age here, things evolve dynamically. And it's a large-scale, upscaled, homogenized treatment of the rheological behavior of the mantle, and we're solving the conservations of the equations of conservation for energy and for mass and for momentum, and we're then analyzing these sort of Earth-like planets from a more fundamental approach. What's sort of in between is a more applied way of thinking at things and assimilating or prescribing parts of the system that we know about. And what's shown here in the middle is a computation by Brad Hager and Rick O'Connell, who was my advisor, where they're pushing plates with what is called a hand of God kind of approach, and then they're computing mantle convection currents within the interior. And we can now do much better than this. Of course, this is a isoviscous computation, but they're sort of a yin and yang, trying to think about the fundamental dynamics, trying to understand what's happening in idealized systems, and trying to use some data and then seeing what works in these models and what doesn't. And it's sort of interesting to move in between. And so that speaks directly to the topic of this meeting, which is, of course, to see how can we combine constraints. And in my case here, those will come mainly from seismology, and then information from mineral physics that tells us how to convert this information from seismology and then say something about the properties we care about, such as temperature. And here on the left are different estimates of what sort of conversions we should use to go from shear wave speed anomalies to temperature anomalies, certain approximations, and then more sophisticated mineral physics estimates is implemented in this Hephaestus tool that I'm going to come back to later. And then we have the seismological observations. Here is some seismic tomography model that are reflecting the ocean continent, this sort of dichotomy at the surface and the top thermal boundary layer, then a whole lot of complicated sort of nothingness in the middle, and then we have the core mantle boundary proximal regions that were discussed yesterday, where we have these more or less coherent large-scale anomalies, and we're trying to sort of make sense of those. Now, what you can do is you can take one of those seismic tomography models and assign a temperature anomaly, assign a rheological strength, a viscosity from it, and then solve these equations and make predictions. And that's what's done here in this particular model, where the plate boundaries are prescribed as weak zones, and then the rest, in this case, the background colors are the geoid anomalies, and then these vectors are predicted plate velocities you can compare to observations. So the geoid is the equipotential surface of Earth that is deflected from the predominantly ellipsoidal shape because of internal density anomalies, and we can link those to the mantle flow. This is a question of estimating the dynamic topography, which is then parsed into density anomalies, and we can solve these things. And so the way this works is that the plate velocities go with the density anomaly divided by the viscosity. We're not solving Navier-Stokes, we're just solving Stokes because stuff is so sluggish, inertia doesn't matter. And so that's a simple Stokes scaling. And things like the geoid or dynamic topography, they scale with the density anomaly only because the viscosity cancels out. And so if we have different constraints, we can try to reduce the uncertainty in these parameters. Now for this particular model, the correlation with plate velocities is about 0.9, and the correlation with the geoid is about 0.8. And there's been decades of work on these sorts of problems, and there's remaining debate as to the contributions from the lower mantle, the upper mantle, and so on. But I think it's a fair statement that we have an understanding of what sorts of ingredients explain the present-day plate tectonic state. By interpreting seismic tomography in a certain way, we get consistent answers. And so the fact that such models work give us some confidence that what we're doing here might be meaningful and gives us some sort of reference model to work off and then mess with it and see how we can break it, how we can use it to understand regional processes, and how we can sort of work our way up then to an evolutionary scenario. And so this becomes quite interesting in a sort of applied sense then for regional applications, right? Where we can use the kinematics trying to understand what structural geology tells us about the evolution of a region, link this with a deep structure, and then try to get closer to this link with a geological record. Now a number of groups have done this over the years, and we've focused on particular sites where there were mountains being formed over the last sort of 100 million years or so throughout the Cenozoic, in particular South America, where the Andes experience various episodes of shortening, and the Himalayas, which is sort of the major orogeny that's happening right now, where the gravitational potential energy that's stored in Tibet is sort of at a balance with the convergent forces, and we have sort of this steady state topography where the mountain wants to flow apart. And if you're asking, well, what are the links with the deep mantle, usually that's a question of asking about subduction, because subduction is the main plate driving force, because the symmetry of convection is broken by the temperature dependence of viscosity as well as the mixed heating regime that we have. And so for South America, you can then sort of reconstruct different episodes of the slab, sinking into the mantle, and you can use tomographic slices for the present day as a record of that history, and then try to bring things back in time. And what we've suggested in both of these places is that the penetration of the slab into the lower mantle was associated with a change in the convective regime, and that is then recorded on the surface in the different episodes of crustal thickening. And so when you zoom out, there appears to be a link that there's sort of a teleconnection between these different orogenic sites, and you can do a cross-section through one of those flow models. And you can see that an upwelling that's associated with this African swell is sort of moving over to the Tethyan belt, and on the other side of the globe we have this Pacific swell that's involved in a circulation that is associated with the Andean orogeny at present. And so you can then think about, well, this is of course a snapshot in time and a reconstruction, but we have an evolution of systems. And what we've suggested is that the initial temporary stagnation of the slab in the upper mantle is associated with a kind of orogeny that is currently seen in places like the Apennines, where we have a one-sided style that we call subduction orogeny, and then once the slab penetrates into the lower mantle, that's when you go into major zones of compression, and then you have a mantle sort of orogeny where you have two symmetric limbs of a convection cell, perhaps assisted by an active upwelling here, leading to the major zones of compression. And then after the slab might be broken off, you go into a stage where you then have organic collapse, and the system sort of forms a cycle on timescales of about 100 million years. And we can look at different realizations at the present day, different origins that might reflect different stages of this scheme. But the point here really is that this is one attempt to really link deep dynamics, which are here exemplified by the interaction of a slab with a transition zone with a continental assembly at the surface. And so to some extent, this brings us back to Arthur Holmes's original vision, who, before the establishment of plate tectonics, not only sort of used radioactive decay for dating of rocks, but he also suggested that mantle convection is the cause of tectonic activity, is the cause not just of plate motions that were really not discussed at the time, though Wegener, of course, had suggested continental drift. But he also linked sort of an evolution in convective cells to the formation of mountains and the emergence of high topography. And so we are trying to put some bells and whistles on this general concept, while recognizing that, regrettably, it's not as simple as in the sketch for sure, but it's also not as simple as a physics experiment, right? So it's not quite as bad as geochemistry, but there are a number of remaining challenges that have sort of been around for quite a while. And so I'd like to discuss some of those and then close the presentation with another zoom in on regional dynamics. And so what are some of these challenges? We heard about many of them already in this meeting, but for me, right, I like to stare at seismic tomography, here shown sort of at the aerial fraction we're really looking at, again, going from the surface to the deep mantle. And so there's no one view of the Earth in terms of the three-dimensional shear wave speed. And so here's an old composite model, and here's a newer full waveform model. And if you see sort of these structures, well, if you take off your glasses, maybe they look fairly similar, but they certainly have a different amplitude. Here converted to temperature, but there's sort of a factor 2 difference here. We're seeing quite a bit of a different structure, including these thermochemical anomalies in the deep mantle, which have different morphology. And so unclear which one is sort of better for what purposes. One way to look at things is in terms of the spectral character, right? If we're not interested in sort of the hand of God approach in specific regions, maybe the character of these models in terms of their heterogeneity distribution should tell us something. And the analysis in terms of the spectral, here characterized in terms of spherical harmonic degree, versus depth structure also has a long record, and I'm showing you here again this composite model, and there's a full waveform model from the Princeton group, and here's a full waveform model from the ETH group. And so you see a number of things. On the right here is the RMS, and you clearly see, while the action is in the top thermal boundary layer, to some extent in the deep thermal boundary layer, the dominance of degree 2, as seen here in this model, is what Bill alluded to yesterday. This is what Adam Jawanski called the pillars of the mantle. And that is to some extent found in these newer models, but it's not as clear. And you can also see that the transition zone here is indicated as exhibits a change in the spectral character in this full waveform model. And anyone know why that is? Jeroen? That's right, because this model started with one of Adam Chabonsky's earlier models, and Adam was a fan of breaking the radial parameterization of models. And so the model that went into this full waveform model starts with a break in the parameterization, starts with a mismatch of anomalies across 660, and the fact that, I don't know, a bazillion CPU hours on the biggest machines and 20 years of computations didn't pull the model away from it is telling us that we have fairly poor constraints on the seismic structure in the Mantle transition zone, which has all been known for a long time. But you have to be quite careful when you're looking at these models that even on our Earth, with all the seismometers, there are persistent challenges in the imaging. Now, what this also means is that these models are quite dissimilar from each other. What I'm showing you on the left here is sort of in roughly chronological order what happens when you G-zip basically the representations of these tomographic models, which I then call the information content. And then here in these diamond symbols, I'm showing the mean correlation of every model with all other models, and here I'm computing the correlation with as mean just because I can. So it doesn't really matter how you do it. The match between models is certainly not increasing over time, and in fact, in sort of this cross-correlation matrix here, the mismatch of some of the earlier models from the sort of late 80s with everything else is about as high as the mismatch with at least one of those full waveform models. And this is, of course, not to say that these new models are wrong or any model is necessarily better, but it's really unclear how much of this additional heterogeneity that is seen in new models is real and how much of it is still governed by theory and data. And things aren't really sort of fully sorted on the mineral physics side either, because if you take the same sort of code, this free energy minimization code by Lars Stixrud in collaboration with Carolina Lithgow-Bertoloni, and you then compute the relative variations in density compared at a scaling factor to go from shear wave variations to density variations, the predicted scaling is about a factor of 2 larger than almost all earlier suggested scalings, and it's this lower scaling here that was used to compute the geoid. And so if you recall, the geoid is directly scaling with the density anomalies, then this would overpredict the geoid, and the problem is even worse if we use the higher amplitude, more modern seismic tomography for reasons I do not understand. We heard in the previous talk about amazing experiments as to the flow strength of rocks, as to the dislocation dynamics, and the scaling of the Stokes velocity, of course, tells us that it's not just the density anomaly, it's also the viscosity we should be worried about if we're trying to figure out how the mantle works. And so for the large-scale models we're doing here, often what is done is we're converting all the complexities of grain boundary sliding, dislocation creep, diffusion creep, to not even an Arrhenius law, but an approximated Arrhenius law, where this is a Frank Kamenetsky approximation of a temperature-dependent viscosity. And so then we have this non-dimensional activational energy, and in one of the more interesting papers, I think, of the last 10 years, Yang and Gurnes used inferences from mantle flow and the geodynamic topography, sort of the kind of stuff that are used in the introduction, to invert for this E. And what they found is that E appears to be preferred to be negative in the lower mantle, which is to say that the regions that we just said we could scale to temperature, like these piles at the core mantle boundary that are presumably hot, would be inferred to not be weaker, but to actually be stronger than the surrounding mantle. How could this be? Well, sort of high viscosity blobs have been suggested, mainly based on geochemical arguments about the absence of mixing of certain reservoirs. A while ago, associated with Bridgmanite, but Balmer and others, and earlier in this meeting, we heard about recent, very exciting imaging of attenuation, and there's also an indication that the attenuation in these blobby regions might actually be higher. So maybe we are seeing strength that is not linked to temperature in a simple way, but there's actually grain size variations or compositional variations in terms of fraction of bridgemanite. But again, the issue here is that it's not a nice physics experiment, and the sorts of constraints we're looking at are not necessarily unique. Quite the opposite. It's often very hard to tease out any behavior on what is large scale, but still remarkably second order. And so here on the top, again, sorry for using a different color scale, is this original model, and that in fact had a temperature dependence that would associate hot regions with being weaker. And here's the same model where I turn it around, inspired by this inversion, and you can see that the correlation values are quite comparable, really. I mean, the model does worse, so we would say, well, this particular computation tells us that this is actually not the case, but my main point here is really this is a challenge, right? How can we infer these large-scale viscosity variations? Not to say that they're not indeed the other way around, but this is a subtle thing, right? And how different is this pattern from the other pattern again? Now, when Victor invited me for maybe a previous version of this meeting, he told me that I should talk about phase transitions. And so I was like, I know nothing about phase transitions, but let me think a little bit about phase transitions. And so for fear of stating things that are maybe too basic, right? So what we're talking about mainly, or here what I'm talking about, are upper Mantle phase transitions. Here's a phase proportion diagram computed again with the Gibbs free energy minimization scheme for hypothetical pyrrolite composition. Sorry, and on the left here, oops, no, so this changed. That's okay. That's fine. On the left here are seismic models, and so here is depth, and here we have wave speed, and in orange here are the estimates from pyrrolite. So this is saying that, well, first off, there's no sort of 1D seismic model, right? So Bill wants to spend $1 billion to map out geochemistry, and we all know, we've known for a long time, well, sort of even the 1D Earth isn't uniquely well constrained. Part of the reason for that is it's a 3D Earth, right? And so it depends what bias is introduced by the sorts of data you're using. We know this particular PREM model is more long wavelength because it's based on normal modes than this AK-135 model, but they're not telling us about the same thing. They are agreeing that there are main steps in velocity at 410 and at 660, but also the match with a prediction or the 1D prediction of one of those mineral physics models isn't like particularly great, and we know quite well it's certainly not good enough to say anything about composition beyond we're somewhere around pyrrolite. You also know that this 1D reference model, the preliminary reference Earth model, it's been preliminary since '84, has two different estimates for shear wave speed, where the propagation for vertically and horizontally polarized waves is different. That is called anisotropy, whereas in physics often sort of cosmic background radiation anisotropy, we would call that heterogeneity, but here anisotropy is the polarization or propagation dependence of wave speeds. I'm going to come back to that, and that's even in a reference model. And up here are the density jumps, and of course they're also different in these models. And so this has been discussed forever, but what the observations show us that, well, slabs indeed make it through 660. We have some sort of style of whole mantle convection, but there's complexity. We've known this since the late 90s, and really nowhere but Central America does a slab go straight through the transition zone. We know it's to do with tectonic reorganization, but a lot of it relates to the phase transition. And so if you take a temperature estimate of a subduction zone, you can then use this Hephaestus package to convert it to a wave speed anomaly, and it gives you some complexity. Excuse me, and you can compute the density anomaly. And so this is the density anomaly. Then at these phase transition is affected by the deflections of the phase transition. One has a positive, the other one a moderately negative Clapeyron slope, and that leads to an assisting density and a resisting density for a cold anomaly, respectively, and the other way around for a slab. And so this gives you here this blue curve, which is the compositional contributions from the phase transition, the extra pole at 410, and sort of hindering shove upward at the 660 and some other in-between effects. And so because we're on the Earth and we have all these seismometers, we don't have to limit ourselves to the transmission sort of imaging. We can also do impedance imaging, or we can look at earthquakes themselves. And we've known for a long time that deep earthquakes, which are found in Wadati-Benioff zones where the slabs subduct, and this is shown in red here, there's a decrease, there's sort of a mid-mantle lull, and then once you're entering 660, you have another increase of seismicity. It's shown here in red for a global catalog, where we can use moment tensors to sort of measure the strain that is released in an earthquake. And it's compared with this compositional anomaly curve in the back, which is blue. And so what we can also do, we can look at the radial strain, how much is being pulled or compressed. And you can see that there's extension at the surface and then compression at depth, which had earlier been used to argue that there's no penetration. Now we know that there's a resistance to flow, but this is flow, going back to the early days of plate tectonics, Isaacs and Molnar. And here's a sort of more complicated thing. That's the average compensated linear vector dipole component of a summation of these moment tensors. And that is indicative of uniaxial average extension and compression respectively. So no volume change, but sort of a different style, no shear kind of deformation. And these things interestingly track the density anomalies. And you can see an effect of the 410 and of perhaps of the 520, and often we maybe don't make use of these constraints as much to sort of link things in an effective sense, right? If you're worried, well, what is the right phase transition? Let's not forget about the deformation we're seeing. But what was done, sort of starting in the mid-'80s, was to explore the role of different phase transitions numerically, and to figure out what sort of settings lend themselves to have whole mantle, and what sort of settings lend themselves to have layered convection. And the answer is, well, we're probably somewhere in between, and we have some degree of impermanent layering, perhaps because of the effects of an increase in viscosity between the upper and the lower mantle, or perhaps because of the effect of a negative phase change. And these models sort of illustrate, they're not really end member cases, sort of two different scenarios. And what you can see is that you have temporary stalling, in particular in the case where you have a strong effect of the negative Clapeyron slope. These slabs eventually penetrate, and the opposite is true when you track the motion of plumes here. On the right are the average viscosity of that model and the average temperature. And you can see that this sort of classic Rayleigh-Benard pattern here is shifted a little because there's a slight amount of temperature-dependent viscosity. And then you can see here, in particular in this case, there's sort of this transient asthenosphere forming. These models do not have any internal heating. That becomes more pronounced in that case. And so my point here is that we've known this for the longest time, and there's a long history of studies exploring this. But there's been a bit of a revival of this sort of intermittency view of mantle convection that goes back to the mid-'90s. And so there's a range of seismological studies where people find things like hot anomalies sitting below the 660, right? Some of the break in character that Adam Jablonski was sort of obsessed about. And so then they're like, oh, what's going on? Well, if you have this transient layering, right, then mixing is incomplete. And at times you might form boundary layers that are temporary in the middle of the mantle, right? And so here's some illustration. This is, Paul is going to talk more about phase transition later in this meeting, but you get interesting things, and we're beginning to perhaps image some of those complex structures. This is work by Tosi in UN, even though these early models used density anomalies that are probably too large, and used estimates for the negativity of the Clapeyron slope that are probably too large when we're considering a multi-mineralic composition. But nonetheless, we're seeing some effects that are akin to these early studies. Now, recently, phase transitions are in vogue again, it seems, and one of the interesting studies was done by Juliana Dunberg's group last year, Lee et al. And what they did is they again used this Hephaestus free energy package that tries to ingest all the sort of laboratory constraints, and they make the point that, well, not only do we have phase transitions, but the phase transitions themselves depend on the potential temperature. And so this plot shows the thermal expansivity as a function of temperature and depth. And what I showed you before was going along sort of this typical ISO geotherm, the adiabat that has a potential temperature of 1600 degrees K. But if you're hotter, as you might be in the early Earth, you're seeing different phase transition, including this sort of insane area here. We have an effectively negative thermal expansivity according to these computations. And so what you find then is that the degree of layering might be particularly pronounced if you're hotter, if your potential temperature is larger, as might be the case in the early Earth. And so there's sort of, again, a recognition that, yeah, it is whole mantle convection, but maybe the pendulum is going back a bit toward the sort of transiently layered state. And so I use this as an illustration that it's not just the phase changes, of course, it's also this uncertainty in rheology that can lead to transients in our tectonic regime. While overall, I think there's good evidence that we had some style of plate tectonics for quite a while, maybe 3.5 billion years or so. It's also clear that tectonics didn't always, or it's quite likely that tectonics didn't always look like the way it looks now in the Cenozoic, and there's plenty of opportunities to have transitions in state. And what I'm showing in the right here is a computation that my student Aaron Hallman did a while back, because we're trying to figure out if we can make transform faults using a damage rheology that includes this memory of deformation. But what she found is that in this particular regime, where slabs are easily damaged, you get interesting interactions between the top and the bottom boundary layer, where the descent of slabs helps determine the location of plumes, and then plumes come back up, guided by the slab, and can sort of punch the slab in the face and shut off convection. And so we have these rheological and phase transition induced complexities at the transition zone that we still need to figure out, and we still have to link them to our understanding of tectonics at the surface. And so it's not just Earth, it's also other planets. And recently, Kerr et al. Did an interesting study where they basically used the Lee et al. Formulation of having a constant entropy implementation of phase changes in this convection code to associate different topographic expressions on Venus with different styles of convection that you see in the layered case. And that layered case of a high potential temperature is more appropriate to consider for the present day Venus, because Venus is in this sort of weird, at least partially stagnant lid state where we don't have the plate boundary somehow breaking the thermally strong lithosphere, and we have some indications of tectonic motions, but certainly not plate tectonics. So maybe Paul will talk about some of the issues involved in this stuff later. Now, as promised, and I think I have another 15 minutes or so, is that right? Yes, perfect. So I'd like to go back to some of those imaging advances that we have thanks to using better theory in seismology. So I'd like to close by discussing a study that I was involved in for North America, for the mantle underneath the sort of North American continental plate. We have a focus on the United States, regrettably, because we rely on data from the EarthScope experiment, and that means our resolution is indeed better across the lower 48. And so what are some of these things we're seeing in the models? And I'm going to get to the details in a second here. So here's an earlier effort by Rob Parrott, my former postdoc, in terms of imaging structure at 250 kilometers depth. Here's this full waveform model that I talked about earlier, showing you some of the information in that model. And here's our recent model, which we call Satona, and that's by Junlin Hua, who is now a professor at USTC. And so you can see that when you sort of go through the depth layers, there's a bunch of structure in these models, right? And for the longest time, I've looked at these models, I'm like, yeah, okay, let's throw them in the trash, and because it's underdamped, it's under-resolved. But talking with Junlin, I guess I was convinced in the end that maybe it's worthwhile to start looking at these second-order features. And of course, people have been doing this for a while, but it's really a change in how we view what is happening underneath continents that remains to be integrated, I think, into our general theory of convection. And so what did we do? Well, we're using full waveform tomography with relying on tools developed by Dmitry Komatic and then further developed in Jeroen Trump's group. Many people rely on the efforts of going back to Dmitry and people who worked on spectral element methods before. We're following sort of a standard approach in terms of the computation, but we do an iterative source inversion. We do structure first and then source, and these are these moment tensor that I mentioned earlier. And what we're doing differently from several other groups is to not look at travel time anomalies, but to look at the correlation coefficient from the waveforms, and that goes back to an approach by Tao et al. In Steve Grant's group. So Steve Grant is the seismologist who's behind most of this, and then Junlin Hua used methods developed by one of Steve's other students. And so this cross-correlation then looks at the waveform, and there's sort of theoretical reason to think, well, this is a terrible idea to look at the cross-correlation, but it turns out that you actually get really good recovery of anomalies such as this hypothetical thing here if you use the cross-correlation. And what is shown here is the recovery using a more typical travel time sort of anomaly, and here's the recovery you get with this cross-correlation one, and this is shown here in terms of the traces. So you're actually trying to fit the traces, right? And so in this particular game, where full waveform inversion has been very common in industry, right? In applied imaging for resources, and has also been used for the last 20 years in regional and in global tomography. The idea is we're going to look at the wiggles, right? We're not going to just identify measurements such as arrivals of P and S waves or measuring fundamental overtones or normal modes. We're trying to extract the full waveform. And I don't think we're quite there yet, but in terms of fully utilizing the spectrum, but it really seems to help for regional applications. And then, of course, you can at least, in theory, turn things around, right, and make it maybe a little bit more interesting and say, well, here's our scientific hypothesis, like the presence or absence of volatiles in a mantle wedge, and turn things around and define new wiggles we should be measuring, right? And we're still in this process where this method has been promising to deliver these new insights, and maybe we're getting there. And the argument here is that it really seems to make a big difference for regional application. And so I talked about the collision of India with Eurasia earlier, where we've used sort of earlier generation seismic tomography as indicated here to link the deep structure with what is happening in the crust and when was the crustal shortening or something like that. And so when you then look at global full waveform models up here, those two are global, and then regional ones, you do see that overall these structures remain the same. That's nice, so maybe the timing story is correct, but then there's significant differences in terms of these small-scale features, which I hope we can begin to interpret. What is striking, and this is work from Liu et al. 2 years ago, is that when you then reanalyze the structures you see, the subduction zones along the western Pacific margin are imaged quite nicely, and there is sort of nothing new here. Perhaps what is new are these hot anomalies that are, that are seen besides the fast anomalies. But then when you look underneath the Tibetan plateau instead, things become sort of quite drippy. The anomaly strength is lower and the morphology is lower, right? And my point here is that maybe it's worthwhile to now really worry about the structure, and maybe we're not looking at noise or under-resolved things, but we're really seeing sort of differences in the response, where you have most of the tectonic deformation being driven by these slabs that are here lying down on 660, doing the things that I mentioned earlier. But then there are interactions, perhaps, with the continental lithosphere that are then reflect in these blob-like structures. And so what Leo et al. Suggest is that there are indeed these discontinuous blobs of lithosphere sinking into the deep mantle, perhaps in association with magmatism in Tibet. There's a correlation between the dripping lithosphere and the stage of magmatism. And my sort of takeaway is, well, we really seem to be seeing these different scales of thermochemical convection, and here we're seeing sort of the mess that a continental lithosphere and continental upper mantle present. So what we did in the study that I was involved in by one, others, is to use the instrumentation from US Array and build a seismic tomography model. That's been done maybe like 50 times, right? But we felt that this particular approach might help us figuring out what sorts of transitions you get between these scales of continental lithosphere and subduction, where in this case subduction is subduction of the Farallon plate over last whatever 100 million years or so, and currently there's like a tiny slab sitting underneath Cascadia, which is sort of the major earthquake and tsunami hazard in the United States. And so here are cross-sections C1, C2, C3, going roughly east-west. On the left here is our earlier efforts to do a variable resolution model, sort of doing what Beavar did in '98 and others for shear waves. Here's one of those global full waveform models, and here's our Satona model, right? And so then we did a bunch of resolution tests. We looked at the actual recovery of the data, things like that, and we feel that the mix of being able to image the slab and getting the lithospheric thickness correct is quite unique in our model. And anyway, we like it, but there are these other features, and there's these weird drippy things that were smeared out in our earlier imaging, but they're still nonetheless somehow connected to the shallower lithosphere. And so there are many anomalies, and these seem to be sitting at the edges of the craton. Now, so what is a craton? It means many things to many people. It's geologically, those are regions that haven't been deformed much for a long time. Geodynamically, that means that they're probably not just lighter and somehow staying at the surface, as expressed by the isopicnic hypothesis put forward by Jordan in, '82, which says, well, they were generated by melting that led to fractionation, that they're intrinsic composition anomalies, but they probably also have to be strong, so just making them light isn't enough to preserve them over long times. Yet we're seeing that they're being messed with, and certainly not the first to see that, but what we are suggesting is that we're seeing sort of a de-blobbing of the craton that is happening right now underneath North America. And so you can look in cross-section again here, A prime, B prime. There's maybe some indication of partial melting along the edges. Edge-driven convection is discussed by Anderson and King and others. And then there's this stuff here, which is dripping, right? Or whatever it is doing. It certainly looks strange. And so what we can do somewhat is to not just look at shear waves, but also look at P-wave anomalies, shown here at depth of 100 and 400 kilometers. And so the difference here is that they both care about the square root of some elastic modulus divided by density, but the moduli involved in P involve the compressibility, and the shear in S just has compressibility. So you're getting sort of complementary constraints on what is happening. And, sometimes we care about velocities, but usually we don't, right? And so the question is then, how can we convert things to something we actually care about, like composition and temperature? That's tricky, but that's when the mineral physics comes in. And what Junlin did is he converted VP and VS to temperature and something like pyrrolite and craton. The way this is done is that he looked at a bunch of samples, he looked at a bunch of published work, and so there's sort of a variation in orthopyroxene content, and we can then convert that, in this case using Perplex, not Hephaestus, to VS, VP, and then estimate what sort of distributions we get in the general region, here, as opposed to this region which is outlined by the dashed line, which we call the cratonic region, and see if those are different. And you can look at the maps, yeah, well, ta-da, S and P do look different, and here's a way to convert this. And so here's the background in terms of VS, VP anomalies, and then compositional and temperature perturbation with depth, some sort of Gaussian distribution. But within this dripping region, already called the dripping region, we have more cratonic material, and the anomalies indicate that things are colder. And here's another way to look at this, where I'm showing you histograms from this cratonic region, and you can see that the perturbation is shifted toward more cratonic and toward lower temperatures. And so that's sort of interesting. So this stuff there, looks cold, but it actually has the signature of the compositionally, maybe perhaps neutrally buoyant cratonic lithosphere. And so we did a bunch of flow computations, and then what you can show is that in terms of the horizontal and the vertical flow averaged from 300 to 500 kilometers, you don't get a whole lot in terms of action if you do not include the lower mantle, so maybe not a big surprise, but what this is saying is that these drips, because of our imaging and because of the logics of the dynamics, they aren't like really necessarily driving things, but they are assisted by a deep mantle anomaly by a prior state of subduction. So you have this two-stage thing where subduction messes with the continental lithosphere, imprints some of this rheological memory, and then sort of sets the stage for later modification of the lithospheric structure, perhaps. And so what might be going on? Well, coming back to these interactions at the transition zone, we might be seeing sort of a signature of secondary scales of volcanism that might be assisted by high volatile storage capacity transition zone. So here's work by Facena and others where we suggested earlier that if you have places where you see volcanism that is not to do with arc volcanism or hotspots, perhaps there's a component of decompression melting that is induced by return flow. And if you have water in the transition zone, maybe you can sustain this sort of process by dewatering. And here's modeling by Richard and Eva Mori building a sort of a detailed model of what might happen, how you might feed water from the transition zone into the asthenosphere, broadly speaking, and maybe even in the uppermost asthenosphere. So there's an interplay here between the phase change and the viscosity increase at 660 and the distribution of volatiles, perhaps, that might lead to volcanism, but also might lead to weakening of the asthenosphere. And what we suggest in this story is that perhaps what we're seeing is this large-scale Farallon slab subduction, maybe with the interaction of a plume from 110 to 70 million years ago, messing with sort of the background asthenosphere where we already have high volatile abundance, and we're then maybe infeeding the volatiles and somehow in some undefined way, perhaps staging the cratonic lithosphere, weakening it so that then if the slab goes into the lower mantle, as it does in the present day, then we're in a stage where we're seeing this sort of dripping that we're now imaging. And despite these remarkably ugly figures, this work was sort of widely appreciated in the news, and the only reason for that, I think, is that this sort of erosion of the lithosphere goes well along with the erosion of democracy and other things in the United States, and it sort of really hit a chord. So it was in the news. People were like, oh look, even the rocks are messed up, right? So, just like the challenges we're seeing right now, for the continental lithosphere, we might be seeing a cyclic behavior, and there's a lot of renewed interest in thinking about the cratons not just as this stationary thing, really, but one that is sort of a setting that's perhaps being rejuvenated. And here's just two examples: work by Wu and others, work by Wang et al., and more recent work by Yang, where somehow, right, we have these, we have here on the left, so that the more common modification of a slab to an oceanic lithosphere, this is not what I talked about, but what you're seeing in the Western US is that there was this previous flat slab episode, and then the removal of the flat slab led to widespread volcanism and a modified lithosphere, which is now deforming much more readily than the rest of the North American continent. And so we have this initial stage of interaction, and then later we have these smaller scale things and perhaps rejuvenation of the continental lithosphere in sort of a cyclic manner. And so how can we do better, right? A lot of the story here is one of, well, of association. It's one of believing the tomography, doing tests that it's okay, using mineral physics to infer compositional and temperature, and then running a few models and thinking about what does this mean about process, but how can we go further? And so coming back to radial anisotropy, we make the case in our study that the presence of relatively strong radial anisotropy, whereas h velocities are faster than sv, in our study area, as is shown here in these cross sections, C and A to B and C to D, that this sort of stuff is associated perhaps with more readily deforming lower continental mantle in a way that was discussed on larger scales by Barbara Romanovitz and others for a long time. But the issue is here that radial anisotropy is even harder to image than isotopic structure. And so here's our earlier stuff where we're saying, well, yeah, VSH is faster than VSV. This psi thing is the squared ratio of the two. Sorry about that, but here it tells you which way it goes. But then you look at other models like this reveal model, and they look very different. And so, again, we know a little bit why that is, but wouldn't it be nice to have a better representation of radial anisotropy? And so the idea here is that, well, the anisotropy reflects deformation. That's because of the alignment of intrinsically anisotropic olivine crystals. So there's some sort of marker and integral of strain reflected in radial anisotropy. And so remains to be seen. And radial anisotropy is, of course, also something that we find mainly in the upper boundary layer. So blue is the anisotropy strength, but we're also, and then not a whole lot throughout the mantle, then perhaps again radial anisotropy in the lowermost mantle. Sort of looping it sort of back here to the deep mantle, what I'm showing you are 4 different seismic tomography models in terms of radial anisotropy strength. And then the outlines here are these thermochemical piles, the LLSVPs, that are really not as blobby as they seem. They're also maybe not just limited to the Pacific and Africa. But what we were excited about when we worked on this earlier is that they look very different in terms of radial anisotropy for some of these models. But then again, they look completely different in terms of sign in other models, and who knows what point here is. There's some information about the history of the piles and not just of the upper mantle. And so what I want to close with, though, is maybe just a comment. I'm gonna skip this, that what we're seeing is the effect of deblobbing, and the rates at which the craton appears to be sinking are sort of borderline where we might see them reflected in the present day deformation of the plate at the surface. And this potentially holds true even for the rates that are detected by geodesy. And so you can look geodetically how fast things are going up and down. And for the most part, what we're seeing in North America are the effects of deglaciation. Those are not trivial to correct for GIA. We can take that out. We can try to take out the viscoelastic cycle effects at earthquakes, and then there appears to be something left over from the deep mantle. But more generally, what is interesting is that the thing that's perhaps most easiest to measure on our planet topography is one that has eluded interpretation for quite a while. We know that the main contribution to topography comes from isostasy, but the thickness and density models you need to correct for them are uncertain, particularly in the continental lithosphere, but there are also dynamic contributions. And so what we are working on right now is to use the evolution of topography, not just from a geodetic perspective, but from a geological perspective, and different flavors of topography to try to fingerprint what is happening for those transitions in slab dynamics and in plume dynamics, and not all going to apply at the same location, but we're hoping to sort of have an integrative fingerprinting approach that lets us read the topography and then bring it together with seismology and mineral physics for the dynamics of the Earth. And sorry for going a little bit over time here. In terms of conclusions, well, we have some idea that we might be able to read the record in terms of transitions in state, but we're seeing these second-order features like the blob-like removal of cratonic lithosphere that appears to be ongoing in the US, which we're only beginning to understand, which remain to be integrated in a full dynamic theory. And sort of subduction, not surprisingly, is the main driver here, but there's several scales in which this oceanic plate system and the recycling of oceanic lithosphere that slabs are part of is talking to the continental lithosphere, and the continental lithosphere is never the same after. Thank you.
Thank you, Thorsten, for this very nice presentation. We have time for a few questions.
Good. You really stirred up the pot here.
Good.
So, I'll ask you one, but I had two burning questions. Early on, you showed us the Holmes diagram of convection. And then you showed what I really thought I like, and I'd like to see more of that surface tectonics enveloped into mantle convection story. But in fact, what you highlighted in that orogenic cycle model was coming from the top, almost going directly down to the bottom and then stirring back up. But then throughout your story, you're showing me what I've been seeing for the last 15 years, which is a lot of people suggesting the slabs bottom out at the transition zone, flux, potentially flux to the lithosphere sitting above it, and then do something. People like Jay Bass like it to hang out in the transition zone. Others like it to slow down. So now I'm going to say, why haven't you revised that diagram that you showed us, the orogenic cycle, and then predict for us better models for surface tectonics down into the deep mantle convection?
Yeah, so I think we're quite vehemently agreeing here, because the diagram was meant to include those effects, and it does have a stalling phase, and that stalling phase we think is very important. So here, that style of orogeny, which is one-sided, you might call it a slab pole orogeny, that is associated with the slab ponding. And only when the slab penetrates do you induce those whole mantle convection currents that then lead to a major zone of compression in the origin. So we are, and so for example, for South America, we've argued that when you look at seismic tomography and you go north to south, you have penetration in the north, but it seems to be absent, not have happened yet in the south. And when you then reconstruct when the slab went into the lower mantle, you can align those times with phases and amounts of crustal shortening. So I think we're on one page here where it's actually indeed slightly improved from Holmes in that we realize that the transition zone is an important modulator. And that transition And it isn't just the style of orogeny, it's also the overall dispersal and assembly of supercontinents that are somehow wrapped up in the dynamics. My point is mainly that even though, right, we've had so much work on the dynamics and the timing, the stalling durations, we are still not really able to forward predict it. No. So these things, right? That's that's geofantasy. But we've actually run models that do just that, and so there is an interplay, right? And so you have here, and this is sort of a mixture between a large-scale upwelling and a small plume. But of course, the system is coupled, right? And in some sense, we're just saying, well, mantle convection causes tectonics, but this is trying to sort of deviate up a little bit. And so the subducting slab will both trigger large-scale return flow and push things to the side, but it might also trigger an instability. The plume would have formed anywhere, but it might be associated with subduction flux. So I think this sort of works out. But yeah, this ponding thing is, you know, tons and tons of papers on it, and if anything, right, the imaging, thanks to US Array, has shown us that there are all these fast anomalies in the mantle that sort of shouldn't be there, right? And people have written papers, well, it seems to have hung out, therefore it's hanging out, right? So it's interesting, I think, that we're still grappling with some of the issues that were around when I was a grad student, but the link to topography and the link to tectonics might provide us some clues, right? And so folks like Paul Hoffman have picked up on this and have sort of tried to link the supercontinental dispersal to changes at the transition zone. And I think that's not something that Holmes thought about. He probably thought about phase transitions, but not in this context.
Yeah. I totally agree that new techniques, new data could advance tomography that Suzanne started like in the late 1990s, that you get more structure. You said that's surprising that you see these little blobby things below the lithosphere. I would argue that that's exactly the expected, I'm going to call them artifacts, but they may be real, they may be, but it's an expected structure that you get if you're going from a regime where your mantle is mostly constrained by surface waves to a part of the mantle where you're starting to get, or you're starting to need the constraints coming from the body waves. And there's an incredibly change in illumination. You're going from from mostly horizontally propagating waves that see the lithosphere really well to a part in the deeper upper mantle, say 300 to 700 kilometers, where your imaging resolution is much, much weaker, and where you're going to be very dependent on how you regularize your model, how you parameterize your model. And so, for example, what I'm seeing here at T3 to D3, I see a lot of oscillations, low, high, low, high, low, high. That is what you expect from regularization if your illumination is not very good. So I would be a little bit careful interpreting the characteristics of the models from lithosphere to deeper upper mantle as due to something that's convective. It might just be the expected artifact from illumination.
I completely agree to the extent that I can, as a backseat sort of seismologist, with the statements as to the well-known differences in the resolving power of body versus surface waves, the well-known differences in the spatial resolution, right? And I tried to make that point earlier. What I would say, though, is that after discussing things with Steve, after staring at these models for a long time, it seems to me that on regional scales, full waveform imaging is really providing us with a different class of models. I'm not saying that all of the blobs here are real, but I'm saying it is maybe not stupid to try to start thinking about what if they're real, right? And what are they telling us about the dynamics underneath the continental lithosphere? And so we tried, of course, in our work, to focus on regions that we think are reasonably well constrained, right? When Junlin was showing me his models for the first time, right? The blobbiness of the craton was sort of subcratonic asthenosphere was not where I was looking for the reasons you spell out, right? Who knows if this is real or not? And I was more like, oh, well, look at the slab here. Look at all these other interesting features. What about this bend here? What is happening here? But look, I'm saying it's worthwhile to think about it, and I wouldn't have said it before the regional full waveform imaging. Is it all real? At least it's not geochemistry.
Romulo, here.
Hi, Thorsten. Yeah, you showed us a lot. Thanks. So about this, I was going to ask you why the blob was blue, but then you said it's because of some orthopyroxene or compositional effects.
It is also
And-
cold, but mix, yeah. A mix.
Well, okay, so if it's cold, it's stiff. Why is it dropping, deforming, and blobbing? And right, it should be red if that's what it's doing.
Yeah, so okay, don't know is the short answer, right? So I think the idea is overall the craton maintains its strength, and on smaller scales you can de-blob these little chunks which are inherently stronger, and water, right, and which you're going to talk about in your presentation maybe, and you've worked on for a long time, appears to play a role. And our argument is that, yeah, it's strong, but it's not as strong as the upper levels, and the concentration of radial anisotropy in those regions tells us somehow that the lower part of the craton appears to be deforming. In detail, right, have we done, I mean, we've done models where we put a craton in and we put a blob beneath, and then once you have that circulation, it's easier to de-blob. So I could generate a model that does that, but I don't think we could learn much because I will have tuned it such that it works. And it wouldn't be stupid to do it, but I think working in the topography, that will really help us in terms of putting the rates of sinking into context, and that should put a stronger constraint on things. And the issue is, of course, we're borderline, again, we're borderline at the detectability, but we think we can get there. We're doing a better job with correcting for GIA. So the short answer is, yeah, I mean, to be determined.
Hey, very nice talk. Romulo from the south of Brazil. Last year, you had some, well, in fact, you had data for a long time, and you published this paper last year about the the plate in the south of the South America. We are working with the Patagonia, so you have the effect of the slab that's going inside. And from the south, we observed some kind of sort of a very pristine noble gas data. So it suggests that, okay, the conclusion was, okay, you have this noble gas data that's suggesting us that this slab was inside of already reached the lower mantle. So because you have this kind of gas, blah, blah, blah. And okay, it was published. But I have one question in terms of geochemistry. So as we have this very pristine composition of the neon, for example, it's not published yet, and I'm thinking really about this because you have this pristine composition of the neon. Is there any possibility to preserve any kind of a pristine composition of the Earth in the even though you have all of this complexity of this what's happening down there, or it's just a gas? I mean, it's just for example, if you mix 2 or 3 end members, by lucky you reach this kind of pristine composition, but it's not pristine itself. It's just a composition based on mixing things. I don't know if it's clear, the question.
I take it I'll interpret the question as being a question to the survival of reservoirs. And that is also wrapped up in this question of what are slabs doing at the transition zone, because as geodynamicists, I do not think we can provide an accurate prediction for the vertical mass transport through 660 over Earth's history. I mean, we can come up with numbers, but they're uncertain, and that's because we don't know how the stalling really works. We know it's to do with rollback and all these other parameters, but we can't really do it. Now, the persistence, right, of thermochemical anomalies, just like all of convection, is controlled by the density and the viscosity. And we know that as a function of the compositional buoyancy and as a function of viscosity, heterogeneities can form different morphologies. For example, they can be in a layer, they can be in a pile. Paul has done a lot of work on how this works out, and they can be in blobs, right? Blobs are not really the favorite solution here, but what blobs do for you, if they're strong, they avoid the shearing of a convection cell, and they sort of naturally self-isolate. So if you're a chunk of reservoir that happens to be strong, maybe because you have more Bridgmanite, as Ballmer and others have argued, then if you're a chunk, then you go, well, let me get away from an upwelling and a downwelling, and you can have longer preservation. But it comes down, from a geodynamic perspective, to the mixing efficiency. And there's been a lot of work on that, and I think you can, and it depends on the volume also, right? So you can isolate different. So I personally think that it's not unreasonable to think that some of these hot anomalies in the deep mantle are associated with isolated geochemical reservoirs, right? These things here. And there are, of course, established relationships between the plume signatures and a bunch of these relationships going back, right, to the Hartz-Dupal anomaly and so on. So my answer is, well, depends. And what I'm sort of kicking it back to the geochemists is that even though we have a good understanding of how, you know, the elemental concentration arise from taking bulk silicate earth and melting it and producing morbs, I feel like we could be doing more in terms of going back to the fluxes and figuring out sort of what mixing relationships are consistent with that. And that's been done, but I feel like maybe it's good to revisit in light of some of the other isotope systems. I talk a lot with Matt Jackson about this, and we're like, oh, look, helium does this. I'm like, yeah, okay, but what does that mean for the evolution? And this is not to say that people have not done this, right? Sujoy Mukhopadhyay has been doing this for a long time. But I think there's something where we can revisit the physics of mixing with doing box models, and not just looking at the mean, but also looking at variations, which is something my grad school buddy Jamie Kellogg did, and then Rudge and others expanded on later, but we could be doing more there. So yeah, and I think, yeah, sure, the plume talks to the slab, and you could be sampling one of those reservoirs, and I think it's not implausible.
Let's thank Professor Becker again. And now it's time for the coffee break.